Well, hello again, mathletes. Well, we've been dealing with derivatives, and so now we need to deal with antiderivatives, which is just kind of going the other direction, right? You start with something that is a derivative, and then figure out what you took a derivative of, is basically the idea. So let's start talking first about just what an antiderivative actually is. So let's see here. We got antiderivatives. And really, to look at these, it's almost easier to look at a derivative itself. But let's go ahead and start with the definition. So capital F of x is an antiderivative of a function little f of x if the derivative of big F is equal to little f. Right? So it's something you can take a derivative of to get the function you started with. So let's actually look at an example here before we start talking about how to compute these things. Let's take this for example. So let's say f of x is equal to x squared plus 3x plus 10. G of x is equal to x squared plus 3x minus 22, and h of x is equal to x squared plus 3x. Okay, so let's actually look at the derivative of each one of these. So f prime, let's see, the derivative of x squared is 2x, the derivative of 3x is 3, and the derivative of 10 is 0. So I'm done there. And then here, let's see here, g prime of x is equal to 2x plus 3, and then derivative of 22 is 0. Okay, so that's that. And then h prime of x, let's see here, derivative of x squared is 2x, derivative of 3x is 3, and there's nothing else. Now, if you notice here, each one of these derivatives is identical. And so what that means is that, well, let me scoot a little bit of this out of the way. F, G, and H are all antiderivatives of 2x plus 3. And you notice how they all differ, right? Each one of them, basically, the only thing different is what's at the end of each one of these, the constant term. And so what we end up doing when we start talking about the general antiderivative, right? The one that accounts for that missing constant, because any term that you have constant in any derivative is going to go to 0 when you take it, when you take that derivative. So what we end up doing is we look at the collection of all antiderivatives is called the indefinite integral. Right? Now, here's how this ends up working. The way we note the indefinite integral is this particular sign. If I want to find an antiderivative of f of x, this is the notation we use. It's the integral of f of x dx. And that dx, it starts to make more sense later on. We have some definitions to talk about in something called a Riemann sum that will define that dx. But this represents the collection of all antiderivatives. And if f is a antiderivative, big F, right? If capital F is an antiderivative, what I can say is that the indefinite integral of f of x dx is going to be capital F of x plus some constant, right? So, for example, if I wanted to do this, right, 2x plus 3 dx, if I wanted the integral of 2x plus 3 dx, what we saw up here in the screen above is the one thing that's constant there is the x squared plus 3x. So this is definitely going to have an x squared because that's the integral of 2x. And it's definitely going to have a 3x in here. But I don't know what that constant term might have been. It could be a 0, which means I'm done right now, or it could be some other number. But I have to account for it by putting a plus c, just so that we know that constant is there. Right, so whenever I'm taking an indefinite integral, you always have to put a plus c on there. I'm sure if you hunt around on the internet long enough, you can even find jokes about plus c. Okay, now some things that are kind of nice about this operation, this indefinite integral, which is really the reverse direction of a derivative. If I happen to have, and these are actually some what are they called? The linear transformation properties or linear properties. Right, there's some linear properties of integrals. One, if I am taking the integral of the sum of two functions, I can split that up. Right, just like derivatives, I can split derivatives up. Right, if they're being added, I can also split up integrals. Right, so if I have something with more than one term, I can take the integral term by term. The other thing that's really nice is that if I have the integral of some constant times a function, excuse me, if I have the integral of some constant times a function, what I can do is the same thing as I do with derivatives, is I can pull that constant through the integration. So I get k times the integral of f of x. Right? So it's pretty straightforward. Now, there are some other properties that are kind of nice. The first one, and probably the one that you'll be using the most right now anyways, is that there are certain things that happen. For example, if I look at the integral, and this is actually a different property, the indefinite integral of x to the n dx. And since we deal with polynomials quite regularly, this is one of those things. You might have an x cubed, an x squared, an x to the fifth, whatever. Those things pop up a lot when you're taking integrals. What ends up happening is, if you think about what the power rule was for derivatives, right? You moved the exponent down to the front and then reduced the exponent by 1. Okay, well, we do that in the opposite direction now. So we're going to we're going to increase the exponent by 1 and then divide by that new exponent. And so basically, if I increase the exponent by 1, I have an n plus 1 here, but I also have to divide by the n plus 1, and I have to throw a plus c on here. Right, and so what that means is if I'm integrating something like x cubed dx, I'm going to increase the exponent by 1 and then divide by the new exponent. And then I have to have a plus c in here. Right, we always have that constant hanging out. We're going to learn how to find that constant here shortly. Right, if I have the integral of x squared dx, I end up with x cubed over 3 plus a constant, right? And the reason that you end up with those fractions, let's see here, let's scoot this, let's make myself a little more room here. If I decide to just, I don't know, let's take x to the 4th over 4, right? Let's say I wanted to take a derivative just to verify that its derivative actually is x cubed, right? So if I'm trying to take this derivative here, let's see. I don't have to worry about the 1/4. I can pull that out and just take the derivative of x to the 4th, which would be 4x cubed. And this is where the over 4 comes in, because when I take that derivative, it needs to have something to cancel out so I can just get x cubed back. Oh, I don't need the constant there. Right? And so that's why you end up with this particular formula. And this is going to be the one that you're probably going to get the most mileage out of in this section anyhow. The other thing that you'll be doing is some of the trig derivatives, and those trig integrals. And the trig integrals are based on the trig derivatives. So it's the trig derivatives we already know, but we're writing them in reverse, right? And so in addition to, let's see if I have enough room here, scoot this up. This idea that the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus constant. In addition to that, we can actually say a few other things. And you can verify these by taking the derivative of the right-hand side to see if you get the left-hand side. The derivative of sine times some constant, sine of some constant times x is going to end up being negative 1 over k, whatever that constant is, cosine kx plus a constant. If I take the integral of cosine kx dx, this is going to be 1 over k times sine of kx plus a constant. Now those guys right there, you have to know those by heart. Those are probably the most important ones that you're going to see. These three right here. So you need to know those. And you'll find if I take the derivative of what's on this side, what I should get is what's on this side. So that would be a good exercise for you to just double check these things. Now, some other ones that might be useful. Let's see here. I jotted them down here. Let's see. The integral of secant squared times kx. Oh, dx is going to be 1 over k tangent kx plus a constant. Oops, there we go. The integral of cosecant squared kx dx is going to be negative 1 over k. And that negative just has to do with that alternating sign in the derivatives of sine and cosine. Not cosine, cotangent. Cotangent kx plus a constant. Let's see what else we got here. The integral of secant x times tangent x dx is going to be 1 over k times secant kx plus a constant. And lastly, kx there. I'm going to rewrite that. That's secant kx tangent kx dx. There we go. And let's see here. Cosecant kx times cotangent kx is negative 1 over k cosecant kx plus a constant. And again, you can verify all of these by taking the derivative of the right-hand side and finding out that you get the left-hand side. So these are going to be the tools that we're going to be using as we go through this. This is also a list in your book if you want to check that out. It's kind of a nice reference to have in front of you, especially through this. We are going to find out as we go through the next chapter here, we're going to be finding out ways to come up with these without having to just memorize them, right? So there's a few things you have to memorize, but once we have some certain ideas of how to substitute and really how to use the chain rule in reverse, That's really the idea that's going to help us the most with things, is using the chain rule in reverse. Because once we have that, we'll be able to come up with all these antiderivatives and indefinite integrals ourselves. But until then, we just have to know them or have a list. Okay, so the next video is going to have some more concrete examples of how this stuff plays out, and even into some familiar territory. Hopefully, those of you who are taking physics will get to see where some of these formulas in physics come from, having to do with position, velocity, and acceleration, and how you build that from scratch. So there we have it. And so until next time, keep your pencils and your wits sharp. And I'll see you guys in the next video.